All right, guys, let's start off our Physics 30 mock exam here by doing the first 10 questions or so here. Right off the top, we expect when we start the exam on the 25th to likely see a momentum question at first. They don't say anything about the order that they're going to appear, but usually they appear more or less in the order of the units that we did. Now, there's exceptions to that. Sometimes we see a question or a scenario that says use the following information to answer the next 12 questions, and there's a question from unit 1 and a question from our last unit and a question from somewhere in the middle in there. They're not necessarily in order, but usually we start off with momentum. So think momentum when you start off this exam. Risk of a motorist becoming fatally injured in a vehicle collision is reduced when the airbag or seatbelt is used because the airbag or seatbelt does what to the momentum and does what to the stopping force. Hey, there is a very, very good chance that this question in one form or another is going to be asked on your exam on the 25th. Yeah, I don't know whether it's going to be an airbag or whether it's going to be somebody's baseball glove cushioning the impact, or somebody's goalie pads, or somebody bending their legs when they're jumping off of the desk, okay, or whether it's somebody that's a stuntman that's falling off of a building and hitting that big airbag on the ground. I don't know what it's going to look like, but in the end, there is almost certainly going to be a question that talks about a predetermined impulse. When you're stopping, okay, when you're stopping an object. When you're stopping an object, okay, it just said it's a predetermined impulse, right? So it's going to be either A or B as far as the impulse goes. The change in momentum is going to be the same, but you're going to decrease the stopping force. You increase the stopping time, you decrease the stopping force, right? Delta P doesn't change. Delta T goes up. F must mathematically go down. Okay, there is almost 100% chance that you're going to see this question on the exam in one form or another. The answer is always the same. Increase stopping time, decrease force, keep impulse the same. Question number 2, love it. Hey, start off an exam like this, love it. First question, we know we're going to see a question like this. Second question, I don't even know what the second question is yet, but when I look at the second page, I see a force versus time graph. And when I see a force versus time graph, if you think way back to February, you know there's 3 words that should immediately come to your mind. What are they? Yeah, area equals impulse. Impulse equals area. Good. So we want to find the area of this. Notice there's no funny units here. Okay, that's one thing to watch out for, though, because we often do see funny units like kilonewtons or milliseconds. If we do, make sure you convert it. Okay, but in this case, we don't. We know that we're going to find the area is equal to the impulse. We're almost certainly going to have to calculate that area, which is going to represent the impulse. Now, we also have a time here, 1.5 seconds. Okay, talking about 2 time intervals, actually, where we're looking at the first 1 second, and then we're looking at the complete 1.5 second interval. Let's see what we're asked here. Let's get the area, and then let's figure out finally what we're asked for. The speed of the toy car at the end of the 1 second time interval. All right. Yeah, that 1 second thing is pretty important there, actually, right? Because it's not the entire graph. So might be something you want to circle in red or highlight or whatever the case may be. At the end of 1 second, what's the speed? Well, what you got to do here is find the area, but because you're only looking up to 1 second, you're going to find the area only of the first second. So let's say A1 is equal to base times height. The base of that is 1.0 seconds. The height is 8.0 newtons. That gives me an impulse of 8.0 newton seconds. Now, if I want to find the velocity at the end of 1 second, I'm going to set that impulse or that area equal to m times delta v. Now, I believe it says, be careful here, it says up at the top here, it starts at a velocity of 3 meters per second. So one of the common mistakes in this question would be to say 8.0 is equal to the mass, which is given to me as 5 kilograms, times v. 8 divided by 5 is 1.6. Hey, if you do that, look what happens. You get an answer of B, right? But it's the wrong answer. What did I do wrong? It's not m times v, that's momentum. Impulse is m times delta v, right? So we're going to say 8 is equal to 5 times delta v. We're going to say delta v is 1.6. And if it starts at 3 meters per second, then it's going to end up at 4.6 meters per second, which means our answer for this one is B. Sorry. Yeah, you're right. There's another common mistake that I just made myself, right? Okay, the answer is C. The change in velocity was 1.6. Okay, the final velocity would have been, what do we say there? Yeah, the change in velocity was 1.6. Yeah, so the final velocity is 4.6, 3 plus 1.6. Good. Next question says the magnitude of the impulse during the entire 1.5 second. Well, we found the impulse during the first 1 second. So now what we got to do is find the area of this one and then add it. We'll say the area of the second section. It's a triangle, so it's 1/2 base times height. 1/2 of 0.5 times a height of 8 is, I think is that 2? 2? We add 2 plus 8, and it should give me an impulse, a change in momentum of 10 Newton seconds. Oh, I love this, eh? When you see the next, flip the page on page 4, and you see, use the following information to answer the next 7 questions. I don't love that. Okay, I hate it when we see that. Okay, but we got to deal with it. Hey, one little bit of strategy that I would suggest to you, especially when we're dealing with 7 questions and it's spread out over 3 or 4 pages, circle the next 7 questions. Okay, it's easy 3 pages from now to forget that that question goes with that information. So you scroll forward to the next 7 questions, just draw attention to it somehow that it goes back with this information. 3 pages from now, when you're on that 7th question, you might forget to go back to here and you might be, what am I going to do? I don't have enough information. But really, you can go back to here and get the information you need. All right, so this is a type of propulsion engine for a satellite. One type of ion propulsion thrust chamber in the satellite to which it's attached are described below. You got all kinds of stuff going on here. You got electromagnets are used to produce a non-uniform magnetic field directed radially toward the spike. So you can see in the second diagram there, the magnetic field, pretty hard to see it on the picture up here, but you should be able to see it on your photocopy. The magnetic field is directed radially toward this spike. There's a virtual cathode consisting of trapped electrons located at the rear of the thrust chamber. And you can see that labeled right here. Positive xenon ions enter the thrust chamber at the anode. That's the left side. And they accelerate toward the cathode. I see that. They accelerate toward the cathode. There's a thought in my mind there. Charged particles accelerating. EI equals EF. I don't know that I'm going to do that because I don't know what the questions are here. Okay, but it's just a thought that came to my mind. Might want to write down EI equals EF here just as a little reminder in case I forget that later on, in case this becomes relevant. Xenon ions pass through the virtual cathode. They pick up electrons, and neutral xenon atoms fly out the chamber. And then we got some data down there. All right, let's see what we're being asked here in this question. Diagram 2 on the previous page, the direction of the electric field in region Y is. Okay, diagram 2 down here, the direction of the electric field. Well, we got a positive anode over here. We got a cathode over here. The electric field is going to go from positive to negative, right? Electric field always goes from positive to negative. So it's going to be to the right. For question 4, the answer is A. Easy enough to start off. As the xenon ions move, hey, what do you see here? What's this plus mean? Xenon plus, yeah. It's positively charged ion, but how much is the positive charge on it? Yeah, it's plus 1 times the elementary charge. It's going to be 1.6 times 10 to the minus 19 coulombs. Moves through region Y is labeled in diagram 2 on the previous page. They experience both electric and magnetic forces. The direction of the magnetic force that they experience is which way? So as they go through region Y, where's region Y? Down here at the bottom. The magnetic field in region Y, as if you look at this, the magnetic field in region Y is upwards. So as these positive particles, go ahead. So which one well, look at the side you're on. Region Y is down here. The magnetic field is upward. We got a positive particle. Okay, we got a thumb going in the direction of the particle, which is, it says the xenon ions move through the region Y. They're going to move to the right. We got a magnetic field pointing upwards. The force points which way? Using our right-hand rule for deflection, right? Force points, Rucker, out of the page, right? Which is option B. There's a couple things you got to be careful in now, right? Some people look at this and say, well, I don't know, region Y could be down here, up here as well, right? Because it's kind of the same thing. Look, they put an arrow right there. If you're wondering where region Y is, it's where they tell you it is. If you're thinking up here might be region Y as well, listen, what should you go with? The area that they tell you is region Y, or the area that you think may also be region Y? Well, let's go with the one that they tell us is region Y. We know the magnetic field at that point is upward. We know it's positive particles, and we know they're moving to the right. Yep. There's a picture there, and we can see that it's, can't really see in this diagram very well on the board here, but you can see in the picture on your photocopy that it's pointing upward. They also tell us in the information at the top of that page that the magnetic field, somewhere here they tell us, the magnetic field is directed radially toward the spike. No, Kirsten, what's your question there? Yep. Yeah. So you're saying there's a magnetic field here, and there's a magnetic field here? Yeah, there is. But look where they tell me region Y is. They tell me region Y is right here. Yep. There's a magnetic field pointing upward in region Y. Now, what's this called? I don't know. I don't care. Okay, that's not relevant to the question. Okay, they're telling me in this spot right here, the magnetic field is pointing upwards. Now, I know that some people look at this and say, well, it kind of looks like this is the same region, but if there's a conflict there, let's go with what they tell me. Right? They tell me this is region Y. This looks like it could be, but that creates some problems for me. Let's just go with what they tell me instead of trying to assume or guess or whatever. Just go with exactly what they tell me. All right, question 6. A xenon enters the thrust chamber at a negligible speed. The minimum distance between the anode and the cathode that's required to produce the exit speed. The minimum distance. Okay, I'll be honest with you. I see this question, and until I saw that word minimum distance, I thought EI equals EF. Charged particles speed up, right? We're going to say their QV equals 1/2 mv squared. And we're going to solve for the initial potential. And when we do that, we get 153.98 volts. But that's not distance. To find the distance between the anode and the cathode, given the potential difference and given the electric field, if you go back to this page, you can see that the electric field value is 1.0 times 10 to the 4. If we're given final potential or initial potential, which is the same as potential difference, we're given the electric field, we can find the distance pretty easily by just doing this. So fundamentally, it still was a conservation of energy problem, EI equals EF, but we had to tack in something else as well to find what we were actually looking for. The answer for number 6 worked out to be C, 1.5 times 10 to the negative 2 meters. Numerical response 1 says, well, in the thrust chamber, a xenon ion experiences an impulse of what? Well, impulse, right? I like the impulse questions because they're generally pretty straightforward. We know that it's equal to F times delta T. We know that it's equal to M times delta V. Looking for delta P. We got the mass. We got the initial and the final velocity. Okay, we got the final velocity. We just used it in question number 6. The mass is 2.19 times 10 to the minus 25 kilograms, and given to us in that big long page of information. And the change in velocity, the final velocity minus the initial, is 1.5 times 10 to the 4. Do the math there. Works out to be 3.3 times 10 to the minus 21 Newton seconds, or 3321. Question 7 also goes with that information, although it turns out we're not going to actually need that big page of information for this question. So xenon ions reach the virtual cathode at the speed of V1. When xenon collides with a stationary electron, the xenon atom is formed and has a speed of V2. What's the relationship between V2 and V1? What's the concept that just jumps out at you here? When the xenon ion collides with a stationary electron, what jumps out at you here? Conservation of momentum. We see that word collide, it's almost certainly going to be conservation of momentum. So I'm going to say Pi equals Pf. All right, what do we got here? We've got M1 V1I, or in this case, we'll say mass of the ion times the velocity of the ion that they call V1, plus 0, because the electron is at rest, equals the mass of the atom times V2. V2, they're saying, is the final velocity of the atom. Now, if it was my choice, the notation that I would use for this question, M1 V1I plus M2 V2I equals MVF. But it's not my choice. They tell me what V1 is and what V2 is and what subscript I should put beside the mass of the ion and so on. Okay, no big deal. We're going to end up solving for V2 here. When we do, okay, the mass of the atom goes over by dividing, and I get M ion divided by M atom times V1. So the answer for this one would be C. Question number 8, which still goes with that original information a few pages ago. Got some data here, basically, right? And you know what, honestly, we see some information like this where it's just numbers. We kind of breathe a sigh of relief because we know that we're not going to have to do a whole lot of reading here, a whole lot of interpretation. It's probably going to be relatively straightforward if we know how to do the mathematical problems. The length of time in hours that it takes this ion propulsion engine must be in operation to increase the speed by 12.0 meters per second is going to be what? Well, what jumps out at you here? Something should jump out at you here. If you look back to your data, and then you look in the stem of the question, the length of time, I see hours, yeah, I see time. And what else do I see if I look above there? Yeah, I see delta V, I see time, I see delta V. But if I look up here, I see time and force, right? Time and force. Okay, what do you do when you have time and force in the same problem? Now think about this. I don't want you to think too impulsively about it. I want you to be too impulsive about your answer. But what is it? Bailey? What is it? Very good, Bailey. We know that impulse is equal to F times T. But we know that it's also equal to M times delta V. We're looking for T. We've got the mass. We've got the force. We've got delta V. Okay, delta V is 12.0 meters per second. We do the math there. It works out to be, I believe it's 1.5 times 10 to the 5. Oh, this is dirty. I believe that's what it works out to be in seconds. Why is that so dirty? Because how easy is it when you're not thinking very clearly because you're tired and it's your last exam and you know that the next day is grad? How easy is it to just circle D there? Okay, pay attention to the units. When you convert that to hours, divide by 3,600 to get the hours, works out to be 41.7 hours. And number 9. Hey, number 9. To me, is the first really hard question. I think this is a hard question, number 9. And it shouldn't be. When I start reading it, it shouldn't be a hard question. The number of xenon atoms, right away. Number, oh, it's total divided by the amount for 1, right? Total something divided by the amount for 1. Total what? Well, I've got the mass of one xenon atom. Maybe I can use the total mass of the xenon atoms, but I don't know what the total mass is. What am I going to do? Well, I started off by saying Pi equals Pf. I said 0, the initial momentum before the exhaust is released, is 0. M1V1F plus M2V2F. Or the mass of the xenon velocity of the xenon, which goes one way, and the mass of the satellite velocity of the satellite, which goes the other way. I've got this number, I've got this number, and I've got this number. It's given to me somewhere as -1 meters per second. Guess it's given to me right here as 1 meter per second. Solve for the mass of the xenon, the total mass of the xenon, right? This isn't the mass of one atom. This is the total mass of all the xenon. It works out to be 0.16667 kilograms. Now, if I want to find a number, we know that we always take the total something divided by the amount for 1. In this case, the mass. So it would be 0.1667 divided by the mass of one xenon atom, which is 2.19 times 10 to the minus 25, which equals 7.6 times 10 to the 23.